All right, concavity of a graph. If a graph of f lies above all its tangent lines on an interval, then it's called concave upward. Here's an example of one. If we would draw in these tangent lines, no matter where we draw them, the whole graph always lies above those tangent lines. So we would call this an example of a graph that is concave up. If the graph lies below all its tangent lines, that's concave down. So no matter where I draw these tangent lines on this graph, the graph's always below. So we would say that this graph is always concave down. So that that kind of upward kind of U shape is concave up. The downward one is concave down. Here's an example of a graph that has some intervals. They want us to say, where's it concave up, down? Here, the whole time, it's kind of that arch shape. Somewhere in here, it changes. And so we'd say concave down here. Now it appears that it's that U shape, so it's concave up. But somewhere again in here, it changes. So here it's concave up. Back down to that other shape, but then again, here it changes. This is concave down, but now it's back to concave up. Now at this point, right here, does it change? Well, no, this is still kind of that same U shape, even though it's going the other way. But again, somewhere in here, it changes again. So this would all be concave up, and then we're back to concave down. One way to remember which ways each is these little smiley faces. So if you draw out this little smiley face here with positives in the eyes, this shape of the smile, that's concave up. If you have kind of this negative here and then the frown, that's concave down. So if you want to have the little smiling frowny face as your ways to remember, you can do that. Also, those points where they change, those are called inflection points. So these points here where it was changing from concave up to concave down, that's an inflection point. This would be an inflection point. So those points where they change from concave up to concave down, here would be another example of an inflection point. This point, because it's a corner, it does change, but we would not consider that an inflection point because it doesn't have a derivative. All right, so how do we find that with derivatives or rate of change? Concavity looks at the rate of change of a rate of change. So where that's positive, where you have positive greater than 0, anytime your second derivative is greater than 0, that's where you're going to be concave up. And again, that's our smiley face here. Anytime you are negative, less than 0, there's our negative again. That's where you're going to be concave down. All right, where it equals 0, where your second derivative equals 0, that's where you're going to have your inflection point. So where it's actually equal to 0, that's our inflection point. Let's look at an example here. This shows the population of the Cyprian honeybees raised in an apiary. How does the rate of population increase over time? When is this rate the highest? Over what intervals is P concave up and concave down? Well, let's look here. I think we can come up with concave up and concave down. Here it looks like, here's our kind of smiley here. So it's that kind of smiley. Somewhere in here it changes. And now we got more of that frowny here. So the looks like somewhere probably right around 12, I would guess. This is concave up here, and then it changes to concave down. When is it increasing the highest or fastest? That would be at this point, which would be our inflection point. So that's where this line would be slanting up the highest, because now the tangent lines start decreasing here also in here, they're not as steep. Here's the steepest part. So at this time right here at 12 weeks, that's when the rate is increasing the fastest. This is an example we're going to look at later called logistical growth. If in a certain environment, your population can't keep growing forever, and so it's going to naturally kind of do this exponential increase. But as you start, it can't keep increasing up this way forever because you would run out of resources. The bees wouldn't be able to survive. There wouldn't be enough like pollen and stuff for it to go. So as it gets to some point in its environment where it kind of starts getting limited, it still grows, just not as fast, and it'll tend off to whatever that carrying capacity it's called would be. So here it looks like carrying capacity might be around 80. We're going to see later that your inflection point, or the point where it increases most, is actually half of that carrying capacity. So if we go over, yeah, it does look that about around 12 weeks would be where it's growing fastest. And that's where calculus can be used to, people in the DNR and stuff can use data to collect and then kind of see what populations are doing based off of that.